Okay, so sound is a wave, which means, of course, that it has the same properties um, and physical aspects of any other wave. So, uh, particularly, sound has frequency, amplitude, and it experiences reflection when it hits a solid surface. Um, so, all of those things are true about every wave, and they are true about sound as well. So, the question, though, is what do we typically call frequency, amplitude, and reflection? And we don't usually call them that when we're talking about sound, though scientists would. But in common speech, we call those things pitch. Frequency is called pitch, amplitude is called volume, and reflection is called an echo. All right. So I just included a couple pictures here. This is a siren, which will help you think about frequency or pitch. High pitch siren, low pitch siren, right? It changes frequency, changes pitch. All right. This guy has a loudspeaker, or whatever you call those things, a handheld voice amplifier. So that is making his voice louder, so that's to help you think about volume and amplitude. So that's basically the, anyway, that refers to amplitude and loudness or volume. All right, so let's move on. Frequency or pitch. Well, we just said this. The frequency of the sound is determined, well, the pitch of the sound is determined by its frequency. So a low frequency sound, such as this one, by the way, these, of course, sound does not look like this because sound is not a transverse wave, it's a longitudinal wave. But if I was graphing sound pressure, this might be a compression here, and this would be, this would be a rarefaction, and this would be a compression, right? Low pressure is a rarefaction, high pressure is a compression. So if we graph sound pressure, we get like a sine wave, sort of a graph. So this is not what sound waves look like. All right, this is not what sound waves look like. This is a graph of sound pressure. So anyways, this would be a low frequency because the wavelengths are large and spread out, so there's going to be fewer waves per second. That means a lower frequency and a lower pitch. Now higher frequency, higher pitch. So high frequency, low frequency. Alright, so human voice is capable of generating several different frequencies, and we're capable of hearing quite a few different frequencies, as we already talked about. So, pitch. Alright, what's the pitch of something? It's basically its frequency. Okay? Amplitude. How much pressure is there in those compressions? Well, that determines the amplitude of the sound. So if there is a higher pressure in the compressions, then that is a bigger amplitude. The little molecules are squished closer together. There are lots and lots and lots of little ones all together in the compression. Then that is a higher amplitude, and that's going to be a louder sound. So again, if we graph sound pressure, if there's a particular complex sound, it might look something like this, varying with time. This could even be a single pitch, a siren of a single pitch, but that's increasing and decreasing in volume, maybe like a tornado siren or something. But in any case, you can see that the sound pressure levels are going up and down, up and down, up and down, but they're going up and down more in this area and less in this area. So this would be louder, and this would be quieter. All right, if we look at this one, here we have a loud sound, and then here we have basically no sound. It would go loud, 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 just like that. All right, and then almost nothing here. So, anyways, that's the idea. Amplitude of the sound wave, or the amount of compression the amount of pressure that's in the compressions, is related to the amplitude, and that's related to the volume. All right, louder sound, bigger amplitude. Now, when sounds echo, that's reflection of the sound wave off of a surface that it can't penetrate easily. So perhaps solid rock or a wall or a desk or something like that. Who knows? Sound might bounce off of those things, and then it would be reflected. Now, the production of an actual audible echo, one that you could hear, is a little bit more complicated, but we're going to just talk briefly about how this happens. It's the same way that anything reflects off anything else, light or even physical objects bouncing off of another object. Same basic principle, okay? A sound wave is produced, it travels, it bounces off some object, and it goes back the way it came. So the original wave goes this way, reflected wave goes that way. The original wave is, in this image, it's pictured as being red, and the reflected wave is pictured as green. How is this used? Well, sound echoes are used in a lot of different ways. They're used for ultrasounds, for example, which we talked about in a previous video. They're also used for things like mapping the seafloor. If you have a boat that just drives, a boat that that sails across the ocean and then sends sound signals down to the floor of the ocean. Those sound signals bounce back, and then if you know the speed of the sound in the water, then you can figure out how far away the bottom of the ocean is, and you can use that to make a map of the bottom of the ocean. It's called echo sounder, an echo sounder for mapping the seafloor. That's pretty cool. Now, in terms of a typical echo that we would talk about for people, there are some restrictions as to how this can occur. For example, I'm sitting in a room right now that's enclosed, and I'm creating this video, but you're not hearing any echoes of my voice bouncing off the walls. Why is that? Well, there are restrictions as to what happens. Why can you sometimes hear an echo, and why can you sometimes not hear an echo? And here's basically the criteria that you need in order to be able to hear an echo. All right, so the echo should be produced usually by a large vertical surface, something like a building, the wall of a building, the side of a mountain, things like that are good at producing echoes. If the echo is less than 1/15 of a second after the original sound, then you're not going to be able to hear it. The echo cannot be detected by the human ear if it is less than 1/15 of a second between the sound and its echo. Also, the surface cannot be too far away from the person who's trying to hear the echo. Otherwise, the echo will lose too much of its energy. It'll become too quiet, and you won't be able to hear it because it's just faded away. Right? So, so the distance then, just to summarize here, the distance should be a minimum of 12 meters and maximum of several hundred meters between the person who's making the sound and then the surface that they're trying to bounce the sound off of. If it's more than a few hundred meters away, it's probably too far, unless you're making a really loud sound. But if it's less than 12 meters, it's literally impossible, because the sound will travel less than 1/15 of a second before it's back at you again, and you will not be able to tell the difference between the original sound and the echo. So the echo sound has to be a minimum, absolute minimum of 12 meters. And to hear an echo at 12 meters would really be something. That would be remarkable. That's really, really close to hear an echo. So those are your criteria for hearing an echo. And then this video has been about pitch, volume, and echoes, and I hope it's been useful and helped you to understand some more things about those terms and how they work in the real world. Thanks for watching, and we'll see you next time.